welcome back. So we are happy to have Renate Loll from Radboud University in person, not from remotely from Naples, and she will tell us about the Lattice quantum gravity theory. Thanks, Renate.
Yeah, thank you for bearing with me, and thank you to Luca and his amazing friends who spare no efforts to bring me here. I, on my part, I've been bummed off several flights, but still I made it. Okay, now let us immediately get started on the theme of why lattices are something very useful, even when you try to do quantum gravity. So here, this is my picture of how we are going to go from traditional lattice QFT to one where we allow space-time to be dynamical. So that's one of the major changes, of course, that have to be made. Okay, now it's about puzzles and insights. So what is the specific puzzle I'm talking about? Well, how do we get to a theory of quantum gravity? Of gravity is space-time and possibly matter, which is this fundamental theory we believe should be there underlying general relativity. So the root of the problem is really the perturbative non-renormalizability of the theory. So that's where quantum gravity lost its innocence in the 70s and 80s, because from there on, the story branches out and things proliferate. So there's option one. We need to go beyond perturbation theory, so emphasis there. But then the question is, how should you do that? And gravity is, of course, really different from other QFTs. Second option, well, a radically new idea. That is, of course, an even bigger Pandora's box. Yeah? And the question is, where do we go? Again, just because perturbative QFT didn't really work out, there is now, seemingly anything goes. But of course, that's where we've been for the last 40 years. It's a birth of quantum gravity approaches, which I put in inverted commas. Yeah. So that means I add extraneous ingredients to just the degrees of freedom and the symmetries of general relativity in order to make a bigger, better theory that becomes quantum gravity or has quantum gravity as part of it. So, of course, that includes all attempts to go beyond pure QFT, for instance, by invoking extended fundamental objects like strings or loops, but also, of course, other things, experimentals, other principles, or abandoning of standard principles of QFT. Now, to cut a very long story short, we've seen 14 years plus of ever more and ever richer approaches going down this option 2 route, largely detached from physical phenomenology, which is, of course, a general application of quantum gravity approaches, but it comes with an extra risk of failure that you are going out because you are unchecked by experiment on some tangents which lead you far away from where you really want to be. Nevertheless, there's a growing wish list of things that people keep writing down. For instance, if you look at J.R. Master's book, Conversations on Quantum Gravity, he extracted several A4 pages, just, what every of his interlocutors, wished quantum gravity to do. He put on a piece of paper, and it comes out as a very, very long list, and of course, well, we could say completely unrealistic compared to where we have been able to go and the type of tools we have at our disposal. Now, today I will, together with the puzzle, the new insight. It's not so new, but it's maybe new to the majority of the quantum gravity community, namely that we've made significant progress on option 1, which is just apply standard QFT tools to quantum gravity by putting gravity on the lattice, but of course getting things right that we didn't get right before, and the major thing being, of course, dealing with dynamical geometry. So let me remind you a little bit of the power and beauty of lattice gauge theory, our primary application of lattice methods in quantum field theory. So it's really the go-to methodology if you want to go beyond perturbation theory. Okay. So, and of course, lattice QCD has been immensely successful since since the 80s. And let me remind you about the general strategy here. So this lattice substituting continuous, typically Minkowski space-time by a lattice is a causal approximation to be thought of as a regulator. So here's an example of a 2D lattice. So the regulator can be thought of here as this lattice spacing. So this is just the edge lengths of these lattice building blocks. And in the end, you always want to shrink this away to 0. So in a controlled way, a continuum or scaling limit, which you do typically near a second order or in the vicinity of a second order phase transition point, while you renormalize their couplings appropriately. So that's, in principle, that's an old and familiar story, but it's a beautiful story. In particular, if everything goes right, you attain universality. That means independence on the details of the lattice discretization, of arbitrary discretization, to set this up in the first place. So the breakthrough in Yang-Mills theory, so QCD of course being a prime application, is really due to Wilson's formulation of the lattice. So this goes back to this very old paper, where one uses as basic variables to talk about the path interval on the lattice, these echelon names. So L is L1, L2, this labels just the one-dimensional edges of this lattice. And then you construct these path-ordered exponentials of the gauge potential. They still transform non-trivially at the endpoints of each edge, namely at all the vertices of this lattice. But the beauty of it is that this residual gauge symmetry is an exact symmetry of the lattice, of the lattice discretization, and that's unusual because we're putting in cutoffs, etc., and they have the nasty habit of destroying gauge and/or space-time symmetries. So this is kind of ingenious to do it this way. And of course, looking at the achievements of Lattice QCD in particular, where one really can make kind of computations of spectra, of course, with highly refined methods that have been improved over the last 45 years. If in quantum gravity we could only achieve a fraction of what people have done there, that would be wonderful progress in quantum gravity. So can it be done? It's not a new idea. Obviously, it's an obvious thing to try, to put gravity on the lattice. And here is my starting point is in my key ingredient will always be the path interval. Here for simplicity, I just look at pure gravity. So where we are integrating over all geometries, so the space of all Lorentzian metrics, modular diffeomorphisms, and with some to be specified measure, and each one will weigh the complex amplitude e to the I as your favorite gravitational action. So this is also called the sum over histories, because these are all kind of curved space-times that you're taking the superposition of. And Lee Smolin in a paper that kind of started what I call lattice quantum gravity 1.0. It was also the start of this career, the very first paper I wrote. Made an attempt to do the same for gravity and outline kind of what challenges this will meet, but also making a very concrete proposal. So I was led to reread this paper because I spoke at his 70th birthday conference just a couple of weeks ago, and I was quite impressed by this, 60-page paper he wrote as a PhD student. So in particular, this quite interesting remarks at the beginning, in the beginning paragraphs of this paper that say, when one begins to think about formulating general relativity on a lattice, one runs into an immediate conceptual difficulty. In general relativity, the geometry of space-time itself is dynamical and subject to quantum fluctuations. And my highlight here, it is difficult to imagine how to make a lattice theory in which the lattice structure itself is dynamical. So this is 1979, so that's, many of you who are not born then. And nevertheless, he makes a concrete suggestion for how gravity in a particular so-called first order formulation, so to make it look like a Yang-Mills theory, might be put on the lattice. And he highlights various key issues, difficulties one runs into. And number one, a measure. You have like say spin connections, but there would be SO3 bond variant. What's the problem? SO3 is a non-compact group, you have a Haar measure, but of course nothing converges. Similarly, for the vierbeins that you need as additional variables in such formulations, they also have they take values in R. So how do you make a proper measure? What should it be? People compactify these things just ad hoc. Well, what does that mean? Is that still gravity? Well, in order to numerically evaluate this very complicated quantity, you will need a Wick rotation, but no Wick rotation is known in the continuum. And when you Wick rotate, well, you run into the problem of the conformal divergence, namely that the action is not bounded below, so how can this ever make sense? And do you see any, well, once you have maybe come up with some suggestions to deal with those, then you still have to try and understand whether you do see you get something that looks like quantum gravity theory. Big elephant, the biggest elephant in the room, I would say, that goes back, this kind of rephrasing of what I've underlined here is really what happened to diffeomorphism symmetry. Right, so we just put this thing on a fixed square lattice and close our eyes and hope everything goes well. But it doesn't, because nothing was ever seen in Monte Carlo simulations of a whole bunch of different types of quantum gravity models. Now, that brings me, not surprisingly, to what I want to call lattice quantum gravity 2.0. Okay. And it took us basically 40 years to work out what are solutions to all these issues. Yeah? I'm not claiming that they're ultimate solutions, but they present a solution that brings you to a workable framework for doing computations. Should it be surprising that it took us 40 years? I don't think it should be, because quantum gravity is hard, right? We've been trying collectively to make sense of it for a long time. So just by putting it on the lattice, it does not become an easy theory, okay? So it's not so surprising. And however, never mind whether we are on the lattice or the continuum, there is this point that I highlighted, from the Snowden paper. There is a problem that standard relativistic QFT has inert background, fixed background space-time, whereas in gravity it should be dynamical. So key number one is what we now know, actually there is a very good methodology to use dynamical curved lattices instead of these rigid things. So that goes, in the Euclidean version, that goes by the name of dynamical triangulation, that was born in critical string theory in the 1980s, but by now it's a causal version of it. So instead of those fixed lattices, spacetimes themselves are represented by kind of triangulations. And here's a little sketch in 2D. One beauty of these triangulations is that, well, they're basically the building blocks you're choosing are basically equilateral, so they're all the same, roughly speaking. So the only thing you need to understand in order to describe one such triangulations is what their gluing relations are, who's the neighbor of who. And then you have data that give you piecewise linear curved space-time, and that you can put into your path integral. And then, of course, in the end, you let with the same logic as in lattice QFT, you send A to 0. In this case, the edges, so the edge lengths. Now, so there are other benefits for putting things on the lattice, whereas in the first place you would have thought, okay, I have a diffeomorphism invariant theory. Putting things on the lattice is the worst thing one can possibly do. But here I now told you the solution is to go to dynamical lattices, and that comes with additional benefits regarding the symmetry of the theory, right? Which is in the continuum, it is the freedom to choose coordinates. And this freedom doesn't bother us really too much classically, but it's just a pain in the neck in the quantum theory because it's a redundancy, and it's a redundancy that's born out of our way to have to choose coordinate systems. So here, we are not having coordinate system, and you could say, as a consequence, what used to be kind of diffeomorphisms now boils down to a relabeling symmetry. Yeah? Of course, we have to call the building block something if you want to do computations with these regularized triangulated spacetime. But it's not coordinates you need and use, but you label them, and this labeling invariance can be taken care of in number one, in an exact way, also computationally in a very simple way. Okay, so that's my second ingredient. The third crucial ingredient in order to make this work is the fact that, again, because of a suitable choice of piecewise flat geometries on this nature, there exists actually Wick rotation, which does not have an analog in the continuum. So it's a Wick rotation really on the geometric degrees of freedom in this regularization. And that enables us now to perform Monte Carlo simulations. And so this is the general methodology, that of course are the language regulations, but really lattice quantum gravity 2.0, or the best version of lattice quantum gravity we have today. And here are a couple of reviews. But I'm just summarizing, of course, the story here in broad brush stroke terms. So what is it? To be a bit more explicit, this is now the form the path integral takes in this lattice version. We sum over triangulated spacetimes T, which have a causal structure. So that is kind of part of what makes these things Lorentzian as opposed to Euclidean, where unfortunately it was shown not to work. So this is our path integral. There is a measure term here, where CT is a number of automorphisms of triangulation. So you can take this to 1 for most purposes. Then we have an interesting bare action, which of course depends on the degrees of freedom by which you describe these triangulations. And it basically is a linear combination of counting variables that count the vertices, the four simplices, and there are two types of the four simplices, which we call N4 ones, by counting those. So you see, the action is basically, it was never easier to evaluate the Einstein-Hilbert action. So this is a kind of discretization. Kappa naught is inverse where Newton constants. The delta is the so-called asymmetry parameter, which becomes, in the non-perturbative region where it's interesting physics, becomes a relevant parameter. In kappa 4 is basically lambda, cosmological constant. Okay? So what we now want to do, we put this, of course, we compute this, and we're looking for a limit. Of course, this is just the regularized version, completely with the same philosophy applied in QFT, lattice QFT. So we send the number of building blocks to infinity, we let the lattice constant shrink to 0, in such a way that there's a finite physical volume. So we study this with quite defined Monte Carlo methods. So what are other constructions that tell us that these came from Lorentzian spacetimes? So we do apply Wick rotation, the one I mentioned on my previous slide. The path integral histories that go into this sum over histories obey a global hyperbolicity. So the topology of the space cannot change as a function of time. We have a very beautiful reflection positivity property of the transformations. That means if we find a continuum theory, it's virtually guaranteed to be unitary. So that's an important property. And yeah, so we can study this now with Monte Carlo simulations. And here is a phase diagram. Yeah? So we tune basically the cosmological constant kappa 4 to a pseudo-critical value because it's easier to simulate a constant flow volume, and then we are left with two free parameters, bare parameters. So in bare inverse Newton constant and this asymmetry parameter, and you see we have a very non-trivial phase structure of 1, 2, 3, 4 phases A, B, C, D, CDS with second order phase transition, another second order phase transition, and first order phase transition. So where this CDS is a so-called disinterface, that's where we see interesting physics with apparently linking to properties of classical gravity. So where we can be fairly sure that seems to be something gravity related. AB for sure isn't relevant. This could be of interest. I don't have time to talk about it here. So this is our disinterface. So not only do we have this disinterface, but we also have, for instance, here this second order phase transition, and this is a natural candidate to try and define a continuum theory. And of course, one can ask, well, what is the UV? What does this give in the UV? Well, our working hypothesis, and something we can also in principle independently check in this calculation framework, is that of asymptotic safety. That is, existence of a non-trivial limiting spectrum. So this is ongoing work, so this is not at all trivial, but in principle, we hope to be able to verify or maybe falsify this conjecture. In the not too distant future, it's not easy because, again, this is background free, one needs suitable observables to make all of these statements. So that is a long story in itself, which you can ask me about this in the question section. So we have this, what are now, you're late, Gerard. What are now interesting things we have computed, right? So that tell us something about the theory. This brings me to the very important subject of observables. Right? Most quantum gravity approaches cannot calculate anything, so they never even reach non-perturbatively, I should say, as a stage of being able to address observables. But this is now handed to us. We have now this framework, so it's interesting to see what happens. So the general form this takes are, of course, observables that are invariant. Yeah? So referring to continuous language, they should be diffeomorphism invariant, and therefore they typically will be of the form of space-time integrals. Yeah? So if I just go back to classical theory, right, this is a manifold, space-time manifold M. Of course, we call the point X is not a physical concept really. If I'm in pure gravity, because I don't know how to mark, it's not marked in any way. So in order to gauge, so R of X, say the Ricci scalar at X, is also therefore not a suitable observable. But if I integrate this, average it over the entire manifold, then this is a good observable in principle. Okay? Now, so observables, we can get already a glimpse, will be quite different in gravity. And that's of course known, if you like. You can already argue for this classically, but here in the quantum theory, it stares you in the face. You have to deal with it. So so I should also say there's more to that than just diffeomorphism symmetry. In this quantum regime, where we find interesting results, the quantum geometry is so non-classical that there is, even if you want to, it's impossible to put coordinates there or to put any reference frames there. So that goes one step beyond there being diffeomorphism symmetry, but then it's also really in the nature of the beast that you have to do without those things. And the beauty is that you can construct observables just from elementary volume and distance measurements, which are available in this framework, and from those you then construct the observables we have seen, and I will discuss in the next slide. Now, here I come now to a really important point, which is the expectation management. Because what I would now call the ground state of this non-perturbative system has I call it a geometry or quantum geometry, is very, very non-classical. So many of the favorite questions you would like quantum gravity to answer cannot be formulated or in an operationally well-defined way in this setting. But again, this is a feature and not a bug. Okay? So therefore, the question is, well, what else is there? Well, is there a problem? Well, I would say it's not a problem, but again, the feature, not a bug. Planckian physics at those scales simply does not conform to our classical intuition, and we have to get used to it. And we have, of course, thought quite deeply about this, and there are nevertheless physically interesting statements we can make about this machine. Okay? So the first one is that of what I call emergent classicality. Okay? So I have these highly quantum fluctuating geometries I suppose in the path integral. And they typically, think of them as a high-dimensional analog of the normal differentiable path of the Wiener measure. Okay? So they're kind of crazy objects locally and individually. Of course, it doesn't stand in the way of having certain observables that make sense in the sense of expectation value and that subsume some kind of averaging. And exactly this is what happens. So, for example, when we measure the global Hausdorff dimension and the spectral dimension on large scales of this quantum geometry, they turn out to be compatible with 4. Okay? You might say, well, that's a triviality. You use 4-dimensional building blocks, but it turns out it's absolutely not a triviality. And moreover, what is an observable we can measure in a relatively straightforward way? It's a 3-dimensional volume of the universe, which is spatially compact, always in our simulations, if you measure that as a function of a proper time that's naturally present there, we can match this to what we call the volume profile of a well-known classical solution of the Einstein equation, namely those of a four-dimensional de Sitter space. So that's very remarkable because we haven't put in any background space. Okay. So it's a cosine cube, if you like, as a function of something that's proportional to cosmological proper time. However, so this is a beautiful result of true emergence in the sense of statistical mechanics. I have microscopic building blocks, and their superposition generates something that macroscopically has new properties, which I didn't put in at the microscopic level. However, you shouldn't be misled to now think that what I've generated there in my computer is a de Sitter space, with line elements. This is typical, just cosmology. Because we haven't shown at all that this thing is homogeneous and isotropic. Not at all. So it still looks, if you look at it locally, like this, and not like something that's a nice kind of geometry. So it's still a very different ballgame. So that's, I would say, even more remarkable. We find this match to this de Sitter shape. But what about more local observables? Are there any? Do they exist at all? Because I have to average in the quantum theory. Well, the first kind of quantum signature that truly says something about the local structure of this is the measurement of the spectral dimension, which I've already mentioned, which for large scales, for large diffusion times, suggests that this is 4 dimensions, so that's beautiful, that's a classical limit, but for near the Planck scale, it turns out to be more something like 2, which is of course not at all compatible with there being any G mu or any classical background present. So there's a true quantum signature. So there's no G mu which could reproduce this result. Of course, after we found this many years ago, many people have kind of reproduced or tried to reproduce this in other so-called approaches, and it has been even this spectral dimension of 2 at the Planck scale has been conjectured to be reversed. Now, here's something maybe more interesting because it relates more to quantities we are familiar with from standard QFT, namely a 2-point function, a correlator. So, a correlator exists, there are diffeomorphic invariant correlators. However, they are, of course, a bit special objects. This is what I would standardly do. I have some scalar operators, could be the Ricci parameter at a point x and at a point y. Okay, but now I have to make this into a diffuse invariant quantity. This is a formal continuum expression. So what do I have to do? Well, I have to integrate over all y's, I have to integrate over all x's. Okay, but in order to make it interesting, I require that x and y should have a geodesic distance r. Okay, so that everything just depends on this r, and of course, plus I have here my path integrals. So this is a diffuse invariant 2-point function. It's something that in the continuum is of course very, very complicated, but something we can study on the lattice. And we have studied it with standard naive versions of curvature, of course terribly ill-defined, but this is a whole story in itself. So we have something that's called the quantum Ricci curvature that's better behaved. We can put this in here. We then integrate over all these insertion points. And we change this object as a function of r. We've done this in a 2-dimensional toy model together with Jesse van der Duin, my PhD student, and really shown that this has kind of interesting properties of the correlator. In 2D, of course, it's kind of trivial because there is nothing very much to correlate. What I want to point out as an extra feature, here we see in this delta function, there are not just those 2 operators that depend on the magic, but of course there's also the geodesic distance. So this is not a true 2 operator at 2 points, but this whole path in between in some complex way depends also on the magic. Okay, that brings me to my final slide. So what is this story in roughly speaking? So this Lattice quantum gravity 2.0 is a well-defined non-perturbative computational lab that allows us to measure. So I haven't yet told you where it allows us to measure. It's about a range between 2 and 20 Planck lengths. So it's a window near the Planck scale. And of course, we have to be clever to ask the right questions that are meaningful in this window. But it does produce outcomes, numbers, plots, the statistical and systematic analysis. So it's really like running experiments on this quantum space-time, which enable us to extract predictions. So, what are some of the predictions? Well, one of the predictions is that space-time has a positively normalized cosmological constant. You can ask, that is inherent in the formalism in a way that it appears to be four-dimensional on sufficiently large scale. It also has an average shape, I have mentioned it already, and also a kind of an average curvature that is compatible with this cluster of zero space in the sense of expectation values, which of course matches our current understanding of the very early universe, pre-inflationary universe. So one lesson is that although almost none of the tools we use, remaining geometry, background is present here, we can nevertheless build observables for elementary distance and volume measurements. It's like rods and clocks in astrophysics, but of course with a very different microscopic world. And this world is also very different from what we're used to on Earth. The beauty is here that in principle, we believe there is a roadmap, because finding this something that looks de Sitter-like, has some aspect in it, is of course very suggestive to try and connect to early universe cosmology, but here from first principles. You see, what one does, of course, in early universe, one assumes that space-time, very early on, is kind of de Sitter-like, with little quantum fluctuations that one just postulates, kind of pulls out of the head. And then, comes inflation, and it then gets all blown up, and we find it as structure in nowadays universe. Well, here we have a chance of maybe from first principles arriving at such a structure and verifying, or maybe also falsifying, or putting more details into what this might have been, this early universe. Although the whole package makes quantum gravity look very much like a strongly coupled system. And the methodology we use is, of course, also that is suitable to those observables. We have scaling behavior, for instance, these dimensions, these dimensionalities are extracted by looking at certain scaling relation. And we have averages, so we might be able to determine things like four laws of propagators, but not detailed analytical objects. And that is very reminiscent of what we find with the condensed matter system otherwise, but much less of what we typically think what quantum gravity is about. So it really gives us a new perspective of what it means to solve quantum gravity. So with that,
all right, we have time for a couple of questions.
Thank you so much for your talk. I was a bit curious about the other phases and how it is that the other phases that you found A, B, C, and how did you come up with the conclusion that this one that you just focused on is the one that represents?
Yeah, so one of the first criteria was really to look at what I call the volume profile, the average of 3 volume as a function of proper time. So we have a proper time parameter in this game. And in these other phases, like if you find something that is very strongly oscillating. Of course, what you imagine should come out, at least on large scale, is something that's four-dimensional. So only the de Sitter phase satisfies that as a criterion, having large-scale four-dimensionality, and possibly there's the second-order phase transition across there. There might be something interesting there, but I wouldn't go into details. But really, so the other phases are already excluded by. So they seem to have absolutely nothing to do with gravity. They are kind of very degenerate geometries, which one has kind of inherited to some extent what one has seen in Euclidean models and precursors of this, where one only ever saw completely degenerate space-times of house of dimension infinite or house of dimension 2, so kind of branch polynomials. So never anything interesting of dimension 4. So it's an experimental finding. Yeah. So we see this, we perform certain experiments where we have certain expectations, at least of large scale behavior like these dimensions, and if those don't fit, then it's probably worthless.
Just a quick follow-up then. Do you understand where the other spaces come from then? It's like a, I don't know, is it a feature of...
Yeah, that's right. Yeah, they come from very strong what I call entropic effects. That means we have these microscopic building blocks, and they are very strong, and you build them together to construct then hopefully macroscopic objects. But they're just some mechanisms. For instance, if your the Newton constant, the kappa 0, is very large, that then they tend to align in these polymeric structures. It's a kind of a remnant of the conformal factor problem. So then these geometries, although the building blocks are of course still four-dimensional, and the geometry at the cutoff scale it still looks four-dimensional. If you zoom out, you just see, oh, it's just branch polymers. That's a nice system one knows many things about, but it's completely useless for a theory of quantum gravity. So it's these, it's truly non-perturbative effects one sees here. So it's kind of, you could say, it's in the measure. There are many, many more ways, depending on where I'm in the space. I can glue from these building blocks totally degenerate objects than there are forming nice objects. Thanks, this was a very good question.
One last, and then
yeah, thank you for the nice talk. I was just wondering, is there any way to get something that's not early universe cosmology, like a black hole, or how would one go about different spacetimes or finding those different spacetimes?
Yeah, I'm afraid that falls under the heading of, well, that's not really, so to first say, when I say this is 2 to 20 Planck lengths, how do I get to this? This is by matching a certain behavior of, in this case, a 3-volume correlator to a semi-classical expectation. That gives me a match between lattice units and physical units. And it turns out, and we've tried this, even when we scan bare parameters in a rather large region, we don't get very much away from these length scales. So they are there. So then the question is, what can I meaningfully ask in this regime? And then typically, people say, oh yeah, what is then the entropy of a black hole in your formulation? Well, I cannot even operationally define many things, like what is a black hole? What does it look like here? What is a horizon? What is an entropy? Yeah, so I'm afraid this is not suited. So that is saying, well, look, this is a feature. We happen to know how to compute in this range, but any other approach to quantum gravity that would also be operational on these length scales would find, I would claim, very much the same issues.
Okay, thank you.
all right. So I would suggest that we now thank Renate again, and we